Hello, this video is on a certain fact about automorphisms of a specific type of extensions by just one element. So as ring theory describes them, they are quotients of polynomials by a maximal ideal by some irreducible polynomial. So we will be interested in looking at the automorphisms of this field, which preserve scaleless elements of K. So that is the automorphism group of the extension f over K, where f is just this field. The result we will get, the description of this as a set, we will get from just sheer ring theory. So let's look at what we are after. We are after bijective maps from f to itself. I will spell out what f is. Again, it's a quotient, in this case, of the polynomial ring. And I'm interested in homomorphisms, which are injective, or surjective, or bijective into f. I will instead look at something which is simpler, homomorphisms just from the polynomial algebra into f, but I will make them aligned with what I'm really after, with the bijective maps from f to itself, by the condition that they lift this map, so that the homomorphisms are really a composition of natural quotient and then homomorphisms I'm interested in. So the condition on this quotient homomorphisms is that they vanish on something which we declare zero in the quotient. So the value on the polynomial of such homomorphisms has to be 0. And then the problem is now to look at descends to the question of what are homomorphisms from polynomials into f. And since we're looking at the case of extensions and k is our fixed elements, our scalars, then there will be a question about homomorphisms of algebras over K. Well, the answer is easy. It's all controlled by the values on this variable t we attach. So the value on t is, well, let's call it somehow, let's call it c, is all we need to know, because everything else will be determined. In particular, this value on the quotient polynomial p will be determined as the value on t substituted in p. So that will be just p of c. And then the condition that it's supposed to vanish is the condition that c is a root. So this little picture gives the answer that, as I said, we can identify our automorphisms. They are labeled by roots of our polynomial p in this extension f. So there will be elements of this extension f which are roots of the polynomial p. As I said, so that is the result which allows us to look inside these extensions, say see which are Galois. So let's again look at this f, which is a quotient of polynomials by this irreducible polynomial p. And we extend our scalars by, so this extension is Galois, if and only if it has a maximal amount of symmetries allowed. So this group has to be as big as it can be, and the size is bounded by the degree. Well, we know what the degree is. It's the degree of the quotient polynomial p. So we just have to see the size of the group, which is the size of this set, to coincide with the degree. Well, let's see what it says. It says that we have as many roots in f as the degree, so p splits. In f. That is, it can be factored as a product of linear terms. I'll just call them c, and then I will look at all such c's which are zeros. So that will have to be possible for a monic polynomial. Let's assume that P is monic irreducible. And hence we have a neat description of when this extension by one element is Galois. Well, it's if and only if the polynomial splits in this extension. The minimal polynomial of this element splits in the extension. In this case, F is called the splitting field. Of the polynomial P. That we will discuss in the future. Now let's look at examples. So we noticed before that not all complex numbers are made equal. Some are algebraic and some are transcendental. Algebraic are nice from the point of view of field theory. They generate finite extensions. Transcendental generate infinite extensions. Let's look at now a finer distinction between algebraic numbers. Again, not all algebraic numbers are equal. Some are nicer, some are more symmetric, some are not. Some generate Galois extensions, some don't. So let's look at the first example, the square root of 2. I'll be looking at this Galois extension of the prime field of the rationals by this square root of 2. So we talked about it before that this extension can be identified with one of those. It is a quotient of the polynomial ring by the minimal annihilating polynomial, the minimal polynomial of the square root of 2, which happens to be t squared minus 2. And so according to our recipe, to calculate the size of the automorphism group of this extension, so let's just call it F. Okay, I'll just call it Q square root 2 over Q. So the size will be the number of elements which are roots of this polynomial. Number of elements in this field. Well, we do have two such. We have plus and minus square root 2. They are both roots of this very polynomial. So the cardinality is 2, and that is the size of our automorphism group, which happens to be the same as the degree. So this is Galois. We can also say what the automorphism group is as a group, being order 2. It is inevitably cyclic. So that is the first example of Galois extension. Let's look at the second example. Let's take a cubic root of 2, also non-rational number, attach it to rationals. Again, we can describe the resulting field as a quotient of the polynomial ring by the minimal polynomial of this, and that will be t cubed minus 2. So to see that this is the minimal polynomial, we could argue that this is irreducible over the rationals, either by Eisenstein or just by absence of roots. So then the same method applies to the automorphism group of this extension. To figure out its size, we need to look into this field and see what are the roots of this polynomial in this field. Well, we still have the cubic root of 2, but that is it, because we know what the numbers in this field are. They are a plus b, the cubic root of 2, plus c, the cubic root of 2 squared, which is the cubic root of 4. A, b, c are arbitrary rational numbers. So none of those numbers will be a root apart from just the cubic root of 2, because we know what the roots are. They're the cubic root of 2, and there are 2 complex roots, and these are all real, so the only one element of this field is a root. So then the size of the automorphism group should be 1, and then the group is trivial. And that is not a Galois extension. It doesn't have any symmetries but the trivial one. So that is it. See you later.